G'day. I'm having another play with Slayer exciters with a 2n2222 transistor, and I've got this one all foiled up for a heatsink. I'll go into that in a minute. And I'm going to show it running on a variety of voltages from 1.2 and 2.4 volts off these AA's here, up to 12 volts across these two 6 volt cells. Right, now, before we get too far into the video, I just want to have a bit of a look at the connections I've got going on over here. This is my main negative ground rail, hooked up to one of those 6 volt batteries, and I also have a clip lead, this one here, that goes all the way across to the negative of these 3 volt batteries, so that it's just to make things quicker when I'm changing connections around. I can move my positive around the place, and the ground connection remains common for the amp metering. Now, to look at the amps, I'm going to be doing it 2 ways in this video. I've got a traditional amp meter multimeter on the 10 amp range hooked up here. I've also got what's marked as a 1 ohm resistor here, but it's actually a 5% accuracy resistor, and it measures at 1.2 ohms. So it throws the readings out a little bit, but we can do the maths later and figure that out. Now, across this resistor, I have these 2 probes here, which are going to be hooked up to my oscilloscope on one channel. So we can actually look at the voltage drop across that resistor at the high speed of the oscilloscope and get a much better idea of what's going on with the amps. And we can then compare that to the reading on the multimeter here and see how accurate the multimeter is, because the multimeter is just giving us an average reading, as you'll see. And so the only things hooked up to this negative terminal are the 2 negatives for my oscilloscope channels and the other negative that joins up to these other batteries over here. Every other time I'm going to be hooking up to the negative rail on the circuit, it'll be going through the multimeter. So this black lead here goes into the common point on the multimeter and comes out the 10 amp circuit on my meter, the 10 amp socket, and that's going to be hooked up to the main negative for the entire circuit. And I've got an extra lead coming off here which we'll be playing with in a minute, and the other red one hooks up down here over to the emitter of my transistor. So I'll switch my scope on, let that boot up, and I'll turn on the backlight for you for a second, and we're going to start out at 1.2 volts. If I can get a decent connection on that, there we go. I'll need to change the values on this scope, and what we can see here is 2 waveforms. We've got our yellow waveform, which is on the collector and coil connection over here on that white clip lead, and that's showing the voltage across the primary coil. And as you can see, the amps are resonating quite a lot, and that's a typical resonating down trumpet waveform. I've got a bit of a double thing going on there and I'm not quite sure why, but as you can see, this straight line across here, that's actually the 0 volts range for that current sensing resistor, and there is some back charge going towards my battery, and we can look at that. The averaged out reading gives us an RMS of 300, that's root mean square measurement, so that's an average of that reading of 320 millivolts, which I think is out by a degree of magnitude because we're reading 38 millivolts on the other meter there. I think that will go more accurate. There we go, 60 millivolts if we change the scale on the multimeter. And if you divide 60 millivolts by the 1.2 ohm resistor, then you should get a pretty close reading to what's on the meter. And this meter's a fancy one. It's currently in DC range. It takes about 3 readings a second, or 6 readings a second or something like that, and averages it. Now, I'm actually going to switch it into a fancy mode, which is for AC and DC measurements. It's a little bit slow to react, but it will give us a slightly more accurate reading. As we can see, there's not a lot of difference there. And because that's slow to react, I'm going to go back to plain old DC metering because it reacts quicker. So on 1.2 volts, we can light up the standard 1n4148 diode Avamenko plug, which is a half-wave rectifier configuration with no antenna whatsoever, but the range isn't fantastic. Also got some germanium diodes which have a much lower forward voltage, and these are also what you call detector diodes. They're used in radios and things like that to make the antenna part send a signal to the rest of the circuit, and they work a little bit better. And if I add an antenna to that, put the clip lead on there, then that goes much, much better. Try and get it in the shot. We can get quite a range off of that one with the antenna. And it does matter where that antenna goes. If I put it way over here, it doesn't work so good. That's actually partly working because I am not connected to earth ground, and it's actually picking up a signal pulsing through these wires. If I connect to earth ground, that probably won't work so well. This coil was originally using a 4-turn primary coil, this one here, but I've had a few issues and I tried a 5-turn coil, which is what I've got on there at the moment, and that does work a little bit better. I think optimum results would come from, say, a 7-turn coil, or maybe even a 11 or a 12. That's about all the action I'm getting off 1.2 volts. I also do get some action off this receiver coil here, which is actually not a very good receiver coil because it's wound in the same direction as the transmitter. And if I give those LEDs the virtual earth of my body, we do get quite a bit of brightness there. And if I grab this spare earth connection, and do pay attention to the current meter when I do this, we can see that we get a really bright connection, and because it's wound in the same direction, the amps go up. If it was wound in the opposite direction, the amps would actually go down a bit, and that's got a pretty good range on it too. You can take that right off camera. And surprisingly, what some people don't realise is that will also work on the positive terminal of the battery. Doesn't need to be earthed. So I can't get any fluorescent action off 1.2 volts. All I'm getting is receivers with a bit of antenna and a half-wave rectifier setup. So let's move up to 2.4 volts. And we can have a look at our scope here. And we can see that primary voltage spikes has jumped up quite a bit. And they're getting peaks of up to 9 volts. Nearly 10 volts there. I'm also getting a 3 volt negative. Now what that is, that's when the, it's down here, that's when the transistor switches off. This little spike here, that's the transistor switching on. When it switches off, we get an EMF collapse which causes the collector end of the coil to go negative, and that will also be causing the other end of that primary coil to go positive, and that's hooked up to the positive of the battery, so that's actually this back charge section here. It's actually putting a tiny bit of charge back into the battery. The amount of joules would be tiny, but what it does seem to do is just excite the battery for a bit, and you do get phenomenally long run times. If you add up the amp hours of your battery and subtract the amps you're seeing from the multimeter over hours, it doesn't work out. Your battery will run for 2 or 3 times as long as it should because of this excitation phase. And quite a lot of people have noticed that. Now on 3 volts we get seriously improved range off these half-wave rectifier Avamenko plugs sort of things. This orange one works really well because the orange LED has a lower forward voltage. It starts up at about 1.8 volts, whereas the white ones need closer to 3. And if I put an antenna off that, it also works really, really well. And that's the reason I'm using a red LED here too. That has a forward voltage of 1.8 volts. I found it works much better than a 3 volt white LED. Especially on the lower voltages, I couldn't get it to work on 1.2 volts with the white LED there. And again, if we have a look at this pulse train on the oscilloscope, the RMS voltage is 180 millivolts, and if we divide that by 1.2 ohms, we get pretty close to what's on the current meter again. Okay, one thing we can see here though that I want to point out, and this is why a lot of people blow their transistors, is look at that max spike. That's saying 7.4 volts. Now if we divide that by 1.2, it's like half an amp spikes going through that little transistor. And the transistor can handle up to 1 amp spikes, but it doesn't like it, and you do need a heat sink if you're going to do it a lot, especially if they're going to be very fast. And all this fast oscillating, you actually see a similar signal. If you look at the base of the transistor, it is working the transistor very hard. So as well as the improved performance with the half-wave rectifiers, we now also get a little bit of light off some fluorescence. This is a burnt out 5 watt globe with the electrodes burnt out. All the circuitry inside probably still works. Maybe it doesn't anymore after being around slayers too much. This is a much bigger 100 watt replacement 15 watt globe. And that lights up fairly well. You can see it does play a bit of havoc with the signal on the scope though. So it is, if you get in too close, you are affecting the performance of your transmitter quite a bit. And we will also notice that, actually in this case, the amps go down, and that does happen with certain loads. If you get a load that resonates correctly, that'll be because of capacitance in the globe. It just makes the whole thing a bit more efficient. And part of the reason for that, you can see if you look at the blue trace, you'll notice the spikes go quite a bit more below the negative line. So the input spikes are about as high, but it's getting a bit more back charge recharging the battery as we're going. And we can light up bigger globes maybe, yep. Light up that big globe. And we can also light up a standard AC fluorescent. This is an 18 watt globe, and again you can see from the black at the ends the electrodes are burnt out. This is one I picked up last week when a neighbour's light blew. And this will just light up around the top centre of the coil. But it is very hard to get it to stay lit up next to the coil. I have been able to get it to light up inside here. I think I'll hold it about halfway. Keep it near the antenna. And slide my hand up. Whoops. And there's something I was going to mention. This is why I've been playing around with my primary coils. If we look at our scope here, the reason that went out is my primary waveforms changed. I've knocked the coil out of tune by shorting. I accidentally bumped the wire at the top. And I can fix that by just touching it near the base down there. And it goes back into tune again. And you can see that if we look at the red LED, when I knock it out of tune, the LED gets a bit dimmer. And when I put it back into tune, the LED gets brighter. So that's one of the reasons that using an LED for a protection diode is a very good idea when you're learning to tune these things, especially when you don't have fancy gear like an oscilloscope. Now, I don't think we can get any incandescent action happening from this voltage. I'll just check again. So I'm hooking this one up to ground at that end, and I'm going to be the positive at the other end. And I'm not getting any action there. I may get a bit of action, yep. A little bit of light in this neon globe. This is a 240 volt neon. I don't have any lower voltage ones handy today. I do get a tiny bit out of that near the top of the coil if it gets really, really close. If you're wondering where I get those from, I get them really cheaply in these $2 cheap shop fluorescent light starters. And if you have a bit of a work around here with a screwdriver, there's no glue or anything in these cheap ones. You can actually pull it apart, and then you also get a nice little reasonably high voltage capacitor. Although I have actually pulled plasma out of this one, it is blown. Got plasma coming out of the corner. You probably won't see it on the camera, but there's a big melted hole in it. So let's move on to 6 volts. And this negative terminal of this second battery is hooked up to the positive of the other one, so I'm just going to hook up there for ease of clip leads. You can see this LED is much brighter again, and I need to scale out the primary voltage on my scope another range. We're now at 5 volts of division. We're looking at a maximum voltage of 24 volts, and we're getting negative voltages of 7.6 volts. So that's reasonably indicative of how much higher than positive the other end of that coil will be going and throwing some back charge in. And we can see that we're getting some pretty significant amp spikes there now. We've got an RMS of 540 millivolts. And again, I may need to scale that out to get a slightly more accurate. No, it's still saying 560 millivolts, so this is where the meter's starting to lie quite a bit. If you divide 560 by 1.2, it's going to be a lot higher than the 2.6 we're seeing on the meter. Or the 260 milliamps we're seeing on the meter. And again, we're getting some back current in here that's actually charging the battery back up a little bit as it's running. And that would actually be causing some desulfatation of the lead acid batteries there too, extending their life and keeping them very happy. I've got a variable resistor down here. It is set to 100 ohms. That doesn't make a lot of difference apart from drawing extra current. If I turn that down, my coil will still stall out if I touch the top. But if you go right down to around that 5 to 10 kilo ohms range, 5 to 10,000 ohms, you can stop that stalling out from happening, but the current goes up quite significantly, and I've burnt a whole bunch of transistors doing that. They're all dead. In case you're wondering how I get the foil on there for the heatsink, this starts to become important from 6 volts and up. There's a dead one from before, and I've super glued on a small amount of foil, and this is heavy duty extra thick foil, and I've wrapped it around about 4 or 5 times with some super glue and squished it on there nice and tight. I've been very careful not to touch the leads with that. And then once I've done that, I get extra pieces of foil and then wrap them around, and you end up with a great big lump like down here. So you've got plenty of heat dissipation. You want good heat conductivity off the transistor into the main bulk of the foil, and then you want lots of surface area for the air to get to. And if I run this transistor without the heatsink at 6 volts, it gets hot pretty quick, and after 5 or 10 minutes run time, the transistor dies of heat. With the foil on here like this, that hardly gets warm at all. That's sitting at room temperature, right? Even I can feel a little bit of warmth right in close to the transistor, maybe 5 or 10 degrees above room temperature, and the rest of the foil's cold. Now, if we go and look near the top of our coil, I can actually now start getting a little bit of plasma. There's actually a tiny little speck there before I get close, which you won't be able to see on the camera. I will try zooming in, but I don't think we're going to see much. There's that top of that coil. It will get bigger as I get my finger close. You can start to see a bit of blue there now. There is a tiny little pinprick there when I get really close. Don't think you can see that. I'm not sure. It's not. The camera doesn't want to play the focusing game. But if I get close enough, my finger or with an earth, it will pull a bit of an arc off there, a bit of corona, and we can also see that with this earth connection. But if I get too close, and I just did, and I stall the tower out into its lower performance mode. It is still running. We do have an amp draw of 100 milliamps, and it will still light up some of these receivers, but the performance isn't as strong. If I touch it down here, it goes back into high performance mode. We'll get much better performance now off the neon. It's starting to light up quite nicely. I'll do that where you can see it. Obviously all these guys start to work quite well indeed. Especially the ones with a bit of antenna on them. I don't even need to touch it up here now. It goes better if I do, but especially because there's a bit of a coil happening there to stop my lead from dangling around everywhere. It's the main reason that coil's there. That works pretty good. And I'm getting a metre or two of range on these when I hold them like this. And if I connect an earth ground, or well, a circuit ground, works even better with an earth ground, we get really bright and huge range. I can plug that into earths across the room and it'll start lighting up 5 or 10 or more metres away. I haven't actually gone around the house yet to discover just how far that goes, but that's pretty bright. That's getting close to full brightness of the LED. As you can see by the way it lights up stuff on the bench. Use that to look at the amps. The other thing I can do now that's really cool, as well as getting pretty good reaction with these fluorescents, I can even do a couple of fluorescents at a time now. Is I can light up this 15 watt 240 volt globe. Now there's a really cool trick here. I can actually make it brighter by placing my other hand close to the coil. Not sure how well you can see that. I've got my leg too close is why. There we go. Sorry about that, my battery went flat again. I think I need new batteries for this camera. So as I was just saying, we get a bit of action on the incandescent there, but only on the 15 watt incandescent. If I switch to this slightly larger 25 watt one, I can't get any action on 6 volts. It just doesn't work. I actually went out specially and spent a whole whopping $2 on a pair of these 15 watters. And if we have a look now at this one, I think you might have noticed there, even without, I've just dropped my coil out of good mode, there are points here where that LED will light up. There it is. I'll zap myself. Try that again. There we go. Without anything connected to either end of the coil. And again, if I had actually wound this coil in the opposite direction, it would work a lot better. I hold on to it, works pretty good. It's in good mode. Yep. That's better. That works really good now. It's definitely full brightness for those LEDs, and that's an anti-parallel pair, so there is AC passing through my body, well over the surface of it due to the frequency. There's no zapping action happening, I don't feel anything at all, no heat, no tingling. And if we put this over here and touch it against, say, our positive lead, it goes really, really bright. And I've just zapped myself with the plasma and knocked it out of resonance. We'll get this in place. Stay you. And that works really, really well. And we can do that on the ground as well. I have been playing around with a piece of foil for a top load. I've tried the can that I've used on this coil before and it's way too much capacitance. It's just loads it up way too much. And I'll place this on here. I will drop it out of resonance doing that, but I can restart it. I'll move that away because it's a bit annoying. And I do get slightly increased performance and range on the fluoros with a top load. That is about the only benefit of it though. And I think you can see just there a slight pulsing happening up and down the coil, up and down the fluorescent, sorry. And that's actually a harmonic frequency of the frequency being transmitted. So this has been on for, I don't know, 5 minutes now. I didn't turn it off when I changed my battery to the spare. And that foil's still cold right at the transistor, But if I didn't have the heatsink on there, it would be getting quite hot by now. The little transistor can't dissipate enough heat on its own. So let's step things up to 12 volts. I'll get this guy out of my way. And we'll go over here to this next battery terminal. Get a good connection. Get it into good mode. You can see stuff like this LED over here now, without even being connected to anything, is lighting up a little bit. And I've got to scale my primary voltage scale right out again. I'm getting voltage spikes of up to 48 volts here, nearly 50 volts. I'm getting negative spikes of 12 volts, indicating that there is most likely charge happening. The other thing we can see is that our amp spikes, I'm seeing 3.2 volt spikes on the amps curve. And depending on what scale, I think my scope's telling a few porcupines there because the resonance going on, it does change around, but we're getting some really big spikes there, way past what that transistor should be able to cope with. Well past, so we really need that heat sink now. And if it's not big enough, I have cooked a few just from heat playing with 12 volts. And I'll just disconnect it and take the... And as you can see, the RMS is 1.2 volts. So again, our multimeter's starting to tell lies, but it's still giving us an indication that we are drawing more current. And we'll go to that fancy mode again. With the higher sample rate. And it's even lower. Not sure what's going on there. It wasn't doing that earlier. Probably something to do with some of these wires floating around the place, receiving a bit of power and telling lies. Now I will just disconnect this to take that top load off. And I'll reconnect it again. Wait good for a sec there and it dropped out of its good resonance. My primary coil is slipping. And there we go, you can now see a bit of plasma up there. And I'll actually unclip my camera. And I don't know if you can hear that, but it's making a lot of noise. If I get my finger in here, as well as getting some EMFs and stuff on the camera. Oops, that's zapping me. And I dropped it out of resonance again. And that's quite a hot plasma too when it gets me. It's a little tiny bit tingly zappy, and it does burn. I get black dots on my fingers. If you hold it there long enough, your fingers will smoke. So let's have a look at the neon. That's going pretty good now. We'll try this one, it's a bit easier to hold on to one of the leads. As you'll notice, as you load it up, the plasma does die off. As you can probably see back here, this disconnected LEDs are lighting up. quite well. If I hold on to them, they go really well. And again, if I carefully stick them on one of my battery terminals, that's really, really bright. That's definitely maximum, or possibly over maximum, but recommended brightness for that LED. We can also now light up the 25 watt globe, and again, if I hold it over here, I can make it go brighter by moving my hand closer to the coil, which also makes the plasma go away. I'm stealing quite a lot of power there. Now, the other cool thing you can do with these Slayer exciters is add a second resonant coil. Now again, I've stuffed up here. I did think that this other coil I had was wound in the other direction. I did intend to wind it in the other direction when I made it, but I've had a close look and it's not wound in the other direction. So that's a bit of a fail on my part. We would get a lot more cool effects if it was wound in the other direction. Now, see if I can get it to connect up here. And you may have noticed some plasma when I connected that to ground. And this one will also give off some plasma, and this is a very hot, high current plasma. It does stall out the system if you touch it too much though. And if we get close enough, we should be able to, provided the bottom of this coil is higher than the primary coil, hopefully we can get a bit of plasma going off both of them. There we go. You can't see that. There is plasma coming off this one and off this one. And this would be a much stronger plasma if I had these coils wound in the opposite direction. And it is different voltage and current. As I think you can see there, that's very yellow, and that really burns spots into my fingers quite quickly. Stalled out. Whereas this one, it's got a higher voltage, it wants to corrode more, and it's not so burny. And the current draw is quite high, even the average current for the little 2n2222 is quite a lot. You definitely need a heatsink when you're doing this. I don't know if I showed that. Fluoros go really, really well now, and you can get a secondary field off the repeater coil. And you can also actually take this repeater coil off the negative side of the circuit. And if I can do this without shorting anything out, it'll run quite nicely on the positive side of the circuit too, and sometimes that works a bit better. And what actually happens here, if you get this right, the voltage spikes across this coil will actually coincide with the current draw, the times of high current draw, and will reduce the load on the battery significantly whilst the coils are resonating with each other, thus improving your performance overall. And it's a matter of playing around with the placement of the coils there for that. Generally a bit of distance works better. And we get these guys just light up from miles away. I'll take that way off camera and it'll still light up. And now the other cool thing we can start to do with 12 volts is pull plasma. This has got a broken filament, the old-fashioned incandescent globe. And we can actually pull some really cool plasma from the inside of that. And these ones are a bit of a challenge to get plasma from. If you want to get that kind of yellow streamy plasma, this type of globe that you find in a microwave or something, I think this is about a 40 watter. There you go, the number's written on there. Yeah, it's half rubbed off. I'm sure it's a 40 watter. It is still work functional, this one. It doesn't have a broken filament. And when things are right, you will get that streamy plasma in these generally before you do. And this one's just a bit of a freak that loves to do plasma. Let's have a closer look at that. And actually, if I carefully get rid of this coil, oops, and even when it's disconnected, I don't know if you see that, that's now disconnected at the bottom end of the coil, and you didn't see it because I zoomed in. Even when it's disconnected, it'll still burn me. And there was smoke coming off that, and I've got burn marks on my finger. So you have to be careful when you handle them. If you pick them up where the wire is, they do bite. I've been burnt a lot of times, and they can be quite nasty deep burns. Now let's have a zoom in on that plasma. And if you're lucky, you can get one of the dangling ends of filament. There we go, to get the plasma off it, and it generates an ion wind and throws itself around like crazy. And you get some really cool effects happening. Now I'll disconnect again. Oh, and that burnt me because that clip lead's dodgy. My current body's acting as an antenna, and I just touched the grounded part. Close enough to ground at 12 volts. Now I'm disconnecting. I'll zoom out for you too so you can see what I'm doing. I'm disconnecting this when I'm playing with the top load at 12 volts because sometimes anything with capacitance hooks up to this antenna on the top, and you get quite a sharp spark across there and it blows out the transistor. So we'll throw that back on top there, and I'll reconnect. And it started up in low mode. And I'll tap it into high mode. And now the plasma works much better off this globe. I can get two streamers at once, no worries. And I've just stalled it. Doesn't like it when I get too close. This top load's probably a bit on the big side. And you can sit here and play with this for hours doing this. It's lots of fun. We might get a bit better action with this globe now. No, just not quite enough juice there to get the big yellow streamers happening. It's getting some tiny little blue dots inside it. And I think that pretty much covers it. There's a Slayer exciter with a 2n2222, everywhere from around a volt up to 12 volts. And my foil is now getting quite warm. Nowhere near transistor cooking territory. Still comfortable to hold. It's probably 20 or 30 degrees above room temperature though. If I do hold my thumb right on the transistor for too long, it's mildly uncomfortable. Nowhere near burning, but you know, it'd be nice if you had cold hands. And we're getting some pretty good range. And of course, if you're playing with a secondary coil such as this one, putting a matching top load on. Oh, and I just arced to my oscilloscope then. Still, it's alive. A matching top load and matching coils, same number of turns in opposite directions, is the way to go. Right, so hopefully that'll help you with your Slayer exciter. If you've been having trouble getting one of these to go. As we saw before in my previous video, I tried doing it with one of these piddly little primary coils, and it's just too narrow a diameter. I did actually have this coil originally wound up with a lot more turns. It's got 800 on it at the moment. I did have 1200 on there before I chopped it down. I took all the extra turns off because it just didn't work. As you get a greater diameter, the things just work better. And that one's also, burning me. It's not connected to anything. I'll see if I can get my finger somewhere where it's not going to zap me, just by holding that too close, and that end's not doing it. Where's the other end of that gone down there? It just welded itself to my finger. I don't know if the camera's catching this, but it does burn me just cruising around. It's also acting as a receiver, and no doubt my performance is being restricted by all the different coils and stuff and random lumps of metal and other things in the room. We've got another little coil back here, which actually does sort of work reasonably well, I think. Oh, I'm in low performance mode again. There we go, I got pink LEDs on that one. And that's arcing two things. But you get the idea. Lots of fun on 12 volts. Let's have another look at this big fluoro. Oh, look at that. That's nowhere near the full brightness it'd be on 240 volts, but it'd certainly light up a dark room. And I can get that, or a bit over a foot away. I'm lighting that up. I'll see if I can get this way. There we go. About 20 to 30 centimetres away, it starts to really die out. If I get close, it gets really bright. That's actually starting to borderline hurt my eyes if I look directly at it bright. Of course, if it was plugged into the wall and working properly, it would really hurt my eyes if I looked directly at it. Alright, that's about it for now. I hope you enjoyed the display. Thanks for watching. Now, very quickly, one last thing I was meant to show. Just using one of these light globes again. Anything connected to earth. Where's my earth gone? I've lost it. I'll get a new one. Anything connected to earth or one of the terminals of the battery. I'll hook that up there. As well as being able to light that up. Oh, I can get, actually that's a poor example. There we go, hold by the glass. I can pull some streams of plasma off my pointy thing near the top lobe. Now be very careful doing this with things with capacitance. I have done silly things like hold one leg of a capacitor and draw arcs off the other leg of the capacitor, particularly high voltage ones. You get too close, you get a spark that discharges the capacitor and it puts way too much power into the base of your transistor and blows it up. Not so frustrating with cheap little 2n2222s, but kind of annoying with more expensive transistors like tip 31s and 41s and stuff. And again, if I get too close, that will stall my tower into low power mode. Alright, that's enough for today. Thanks for watching.